Hey everybody, this is Alex Merced, developer advocate here at Dremio, and what I want to do today is I want to talk a little bit about Apache Iceberg. So basically, I've done sort of an Apache Iceberg 101 series videos before, but things change, so I figured I would just do sort of another sort of run through many of the topics periodically. So basically, I'll try to do this like every quarter, every few months, just do a fresh overview of Apache Iceberg. Okay, so this is my Apache Iceberg overview in May 2023. Okay, so also, me and some of the others are authoring Apache Iceberg, the definitive guide. So you can get an early release copy by scanning this QR code. So if you want to get the book on Apache Iceberg, right now you can get the first, I think it's like 55 pages as of speaking right now. And again, further early release updates will occur. You just scan that QR code and you can start reading that guide that covers a lot of really good stuff. But yeah, let's start with the question of what is Apache Iceberg. So if you're coming to this video, it's because you just kind of want a rundown of what is Apache Iceberg, why Apache Iceberg, etc., etc., etc. Okay, so what Apache Iceberg is, it's a table format. So first, let's just kind of set the stage of like, why do these things matter? Okay, so bottom line is in the world today, the scale of data is expanding. Okay, every day the amount of data that's being generated, the amount of questions we're asking that data are constantly expanding. And not every tool or not any individual tool can handle sort of every use case. So now it's more important that our data can work with multiple tools. And the problem is oftentimes in the data warehouse world, you're kind of just stuck with that particular data warehouse set of tools. Okay, and then on top of it, you have the whole sort of complexity of having to move data from your data lake to the data warehouse. Then you have two copies and all this. So ideally, we can do more and more work from the data lake, where basically that data can be accessible by more than a single set of tools. And again, we're not duplicating the data. So we reduce our costs. We also are going to have a more flexible infrastructure, all that good stuff. So the idea is we always want to do more and more work with the data lake. And so originally in that impetus of wanting to do more and more work with the data lake, you had basically you store the data in like a Hadoop cluster, and basically you had to use this thing called MapReduce to write these Java-based scripts to do analytics, which wasn't the most accessible way of doing things. So eventually someone creates Hive, and Hive allows you to write SQL that then gets converted into these MapReduce jobs. But for Hive to be able to do that, for you to be able to write SQL, there has to be a way to express what is the data set, what is the table, okay? So you have all these data files in your Hadoop cluster or wherever you have your data stored. It could be object storage in modern times. You need a way to say, hey, these 1,000 Parquet files are one, table. And the way that Hive solved this was by saying a particular folder is the data set. Okay, so essentially you would say, hey, this folder is the table, and any subfolders in here are different partitions. And then you had a thing called the Hive metastore that would track, hey, this is the folder this table exists in, and these are the folders that the individual partitions in that table exist in. And that was pretty much what it did. And then what would happen is that an engine that wanted to query that table would get that folder from the Hive metastore and then do file listing operations to list all the files and then read those files in the relevant partitions of that table. The problem is all those file listing operations are expensive because you're listing a bunch of files, probably a lot of files. That takes time to kind of discover where all the files in the directory are, and then to open them up and read them. And overall, it was an expensive way of doing things. And on top of it, it made it really hard to do sort of really a granular atomic updates because you're only tracking at the partition levels, so you could at best do an atomic transaction at the partition level. So rewriting an entire partition to update one row, probably not the most efficient thing to do. So you have all these sort of problems trying to do more with the data lake when you're trying to use a Hive-based table. And this is essentially the issue that Netflix was running into. Okay, it was like, okay, we have these issues. We need a solution that provides more correctness and consistency, faster query planning and execution, that allows users to not have to physically worry about how the data is physically located in the files. Okay, so if like a random file gets added to a directory, it shouldn't magically appear as part of my table. I shouldn't have to think too hard about where these files are physically located. I should be able to change how this table schema works, how its partitioning works. I should be able to change all these things. And I need to do this at scale. A petabyte scale is what Netflix needed. And this is where the fundamental insight, the fundamental idea for Apache Iceberg comes in, where basically if you need to achieve all these things, you need to move away from looking at tables as a bunch of files in a particular directory, but instead as a canonical list of files saying, hey, regardless of where these files are located, these are the files that make up the data in the table. Okay? And that new approach is what allowed Iceberg to solve these problems. Now, what Iceberg is and Iceberg isn't, the Apache Iceberg project really provides two things: a specification, meaning a standard way of writing metadata to define a table. Okay, so any engine, basically any tool for ingesting data, for querying data, can now implement this specification. So basically, by using the specification, any engine can say, hey, I can read the data, because they know how to read the metadata to then read the data. And any can then write to the specification. They have a standard way of writing how the metadata should look like. So that way everybody can interop. Okay, so the idea is everyone follows the specification. Anyone can read an Iceberg table, anyone can write an Iceberg table, because it's all done the same way through an agreed upon standard. Also with the project, to make it easier to adopt the standard are libraries. Over time it'll be in different languages, but right now you have a Java API, which I think right now 1.30 should be being released soon, and a Python API. In the future, you might have like Rust and Go and Apache Iceberg APIs in other languages. The benefit of these APIs is that, let's say the Java API, if I am writing a tool in Java, okay, I can use that Java library to help add Iceberg functionality to my compute engine, to my tool, to whatever. Same thing with the Python API. You can use those to incorporate more Iceberg functionality in there, or you can just use them to work with Iceberg tables directly, particularly for just like, understanding the metadata or writing metadata, things like that. So you have these tools. So essentially, you have the standard, and you have some tools that kind of help you use that standard across the software world. What Iceberg isn't, it's not a storage engine. It's not an actual file type. Okay, so this is different than Parquet. Okay, your Iceberg tables data will still be stored in things like Parquet or ORC or Avro. Iceberg is just, again, a standard way to write metadata, so that way an engine can understand that a bundle of Parquet files or ORC files or Avro files are a singular data set. It's not an execution engine. Okay, Apache Iceberg isn't a way of actually executing queries. It is a standard way of writing things. You would still need some sort of compute engine, like a Dremio or Apache Spark, to actually run queries on the Iceberg table, or to write the Iceberg table. It's not a service. It's not like a piece of software that you have constantly running to do a thing. Okay, you still need other software to write and read to these Iceberg tables. It is just a standard way of what you should write and what your reading should look like as far as the metadata goes. So the idea is a standard. We're standardizing the metadata layer between your data files and your engine. Now, absolutely love the architecture of Apache Iceberg. Again, the more I just like stare at this and think about this, the more genius it is to me. But bottom line is, the way this works is that you break up the journey for how an engine plans a query across several different steps. Okay, going from the catalog all the way to the actual data files. And sort of each layer is going to give an opportunity for the engine to do less work. Because bottom line is, if you want faster queries, there's two ways to get faster queries. You could either throw more compute, meaning faster computers with more memory, which cost more. Okay, so that means you can speed up your queries, but you're going to be paying more. The other way you can speed up queries is by doing less, in the sense that your compute has to read less files, or if we're talking about Parquet files, read less row groups within that file. So the less work the engine has to do, the less compute, so it's less cost, and your query is going to be faster because you're reading less data overall, because less data is relevant to the particular query that you're running. So the aim of Iceberg is to kind of take it a step further, because in Parquet files, again, you can do what's called predicate pushdown and say, hey, this row group's not relevant, this row group's relevant. But there are certain files that are probably the whole file isn't relevant to your query. So with Apache Iceberg, you're going to have this metadata that's going to allow you to determine, hey, these files I need, these files I don't need. So let's kind of talk about like the step that the engine's going to go through. So if I'm a query engine and I'm going to read an Iceberg table, the first step I'm going to do is I'm going to go to the catalog. The catalog could be one of many mechanisms, but essentially it has one particular job. Its job is to be a directory of all your tables. So it'll say, hey, table A, and it's going to say one thing. What is the file path of the current metadata file? Okay, because everything is in the metadata files. The catalog is just there to say, always point to what the most recent metadata file is for that particular table. So table A is pointing to this location. This could be a Hive metastore, because a Hive metastore can contain file paths, because again, it used to contain a directory path for the table and its partition. So you could use a Hive metastore as a Iceberg catalog. You could use something like a Project Nessie, which I'll talk more about later on, as an Iceberg catalog. And there are several other possible catalogs, such as JDBC databases, DynamoDB. There's a thing called the REST catalog, which I'll get into more later on. There's a lot of possibilities of what can be an Apache Iceberg catalog, but it's going to be the thing the engine uses to figure out, hey, this table, its metadata is located here. And once it knows where its location is, it's then going to read the metadata file. And the metadata file is going to have this sort of like more grander table level definition. Like, what is the table's partitioning scheme? What is the table's schema? What are the different table snapshots? So all this sort of higher level macro table definitional stuff is going to be here in this metadata file. So once we know, hey, this is the partitioning of the table, this is the schema of the table, what we need to know is which snapshot we're going to scan, like what point in time. So it could be the most current snapshot, okay, or one of the previous historical snapshots. That's how we enable things like time travel. It basically, when it finds a snapshot that wants to scan, there's going to be a path to that snapshot in a file referred to as a manifest list, okay? So there's manifests and there's manifest lists. So the idea is that a manifest is a group of files that make up the table, okay? Now, an individual snapshot of the table can be made up of one or more of these manifests. And all these are all listed in the manifest list. So each snapshot is essentially a list of all the different groups of files that make up that table at that point in time. Okay, so there's one manifest list per snapshot. So basically, once we know what snapshot we want to scan, we'll go to the manifest list, which has stats for the manifest. So not for an individual file, but for a group of files. And it's going to include things like partition stats. So like, hey, what specific partitioning scheme was this data written with? And two, what are like the partition values? So we can sit there and look at these partitioning stats and say, well, based on the way this table is partitioned, based on what this query is asking for, this particular group of files is not relevant. We're going to prune that. No need to scan this or deal with this any further. So there might be 10 manifests, and using what's called partition pruning, so pruning the data based on the partition value specified in the way the table is partitioned, we can say, hey, out of these 10 manifests, only 7 of them are relevant to my particular query. So now we've just gotten rid of 3 groups of files. Those don't need to be scanned. Then we'll go to each of those individual manifests, and those manifests are going to have a collection of information on each data file that manifest tracks. Okay? Most importantly, it's going to have stats for each individual column in the table, such as how many records are in there, okay, or I mean how many different stats as far as like counts, min and max. So like, what is the range? So basically, hey, we have a height column. This file contains heights between 5'3" and 5'6", things like that. Because then we can take a look at those ranges of column stats and say, well, based on our query and the kind of data that we're looking for, we're only looking for people 6 feet and above. This file only has people between 5'3" and 5'6". That's not relevant to our query, so this data file can be pruned from our query, doesn't need to be scanned. So we can go through each manifest, eliminate every irrelevant data file. So then what happens is that when you get to the end of this process, you have a list of files you need to scan that is the narrowest list of files you need that can possibly have data relevant for your query. Okay, so with this particularly, especially if your data is well partitioned, well sorted, this could mean a tremendous benefit and speed benefit to the actual query because you're reading a lot less files. Okay, so you'll get a faster, cheaper query. So that's just sort of like the main deal. The main deal is it's going to provide you this metadata that's going to allow your query engine, whether it's again Apache Spark or Dremio, to plan that query smarter, faster. To kind of exemplify this, let's take a look at this case study from a Netflix example. So Netflix has this telemetry system called Atlas that was basically, well, let's let the numbers speak for themselves. When you take a look at this table and you ran a query on it as just a Hive table, so the only filtering that was going on is that all the files were being read, but you use Parquet filters, which means, hey, you're skipping row groups based on row group stats, basically for each day's worth of data. And when I say 400,000 splits, to keep it simple, think of it as just more data I need to scan. So the amount of splits you would have to scan for every day's worth of data was 400,000. So not total, for each day's worth of data. Okay, and if you just ran an explain query, which means you didn't actually do the scan, you just ran and planned the scan that you would have done. Okay, it took 9.6 minutes just to plan. Okay, just to plan what you would scan, it took 9.6 minutes. Now, if we change that table over to an Iceberg table with just partition filtering, so that means, hey, we're eliminating individual manifests based on partition stats, but there's no individual file pruning because of the experiment. Okay, that planning time went from 9.6 minutes down to 10 seconds. Okay, much faster planning, and overall you had a much faster query because, again, if it took 9.6 minutes to plan, it would have taken a lot longer to run the query. So in this case, the whole time, including the planning time, was 13 minutes. So it took about 12 minutes and 50 seconds to actually run the query after planning for 10 seconds. Okay, and you see, like, the reason why is because there's a lot less to scan. Instead of 400,000 splits for each day's worth of data, you had 15,000-ish splits total. Okay, again, less stuff you have to scan, the faster the scan, the cheaper the scan. And when you add in the min-max filtering, that's when we assess each individual file and say, hey, am I looking for any data within these column stat ranges? Okay, it took a little bit longer to plan because you're going and you're comparing each of those files, so 25 seconds to plan. But that additional planning time pays off in much quicker query time, 42 seconds total for the whole journey. And you see why? Because there's less data you have to read, 412 splits. Okay, so bottom line is by having all this metadata, it allows you to more smartly kind of narrow down to the narrowest nook of files you have to read. And again, an engine can then take advantage of like things like Parquet row groups to do further filtering from there. Okay, and then Parquet has other advancements you can use, things like Bloom filters and whatnot to give you even further benefits. So beyond performance though, so again, Apache Iceberg will give you better performance, especially if your table is well optimized. Again, at the end of the day, like if you have a poorly sorted table, poorly partitioned table, it'll still be faster than Hive, but again, a well-structured table is going to be really, really fast. Okay, but it also going to allow you to efficiently make smaller updates because you're not having to swap a whole partition to update one record. You can just swap out that one file because you're tracking things at the file level. You have snapshot isolation. So since you were tracking each individual snapshot, you're going to be able to kind of see what happens, which enables time travel. So that means I can go and query a snapshot from the past. Okay, faster planning, as we saw. I have all these layers of metadata, and each layer of metadata allows me to I'm able to get more and more granular, but first, eliminate large chunks of files and start eliminating individual files to get that sort of really faster, smarter planning. Now, these metadata files are also tracking table metrics, okay? And you can derive table metrics from the data in them. So basically, every time you write to the table, your metrics are being updated. So you don't have to worry about stale metrics, which is a problem in Hive, because the Hive metastore is only tracking directories, not statistics. Time travel, we mentioned you can scan previous snapshots. Table evolution, not only can you evolve the schema of the table, okay, so you can add rows, delete rows, change data types of a row, but you can also change the partitioning of the table. So if you're partitioning by year and then later on want to partition by month, you can make that switch without having to rewrite all your data immediately. You may want to, and then you can separately do a compaction job to rewrite those data files, but in the short run, You can change your partitioning scheme. New data will be written to that new partitioning scheme, and you can move forward and enjoy that. And again, all engines, so if I were to make a change in Spark, so Spark, I ingest some data, a new snapshot is created, and then the metadata file is, a new location is created, and that catalog is going to point to the new location of the new metadata file. If I were to immediately do a read in Dremio right afterwards, Dremio would consult that catalog and see that new metadata.json and basically query the data as it is in that new snapshot. So all those changes are immediately visible to any engine that can basically read Iceberg tables. Okay. And then you have asset transactions. Okay. You again basically because of that snapshot isolation, you can say, hey, a new snapshot's only created if the transaction is completed successfully, and if not, then nothing has changed. Okay, so you get those asset guarantees, so that way it's more like a traditional database, but again, instead it's on your data lake, aka data lake house. And you have several different ways you can optimize a table. Like basically, while you can always optimize it manually, Iceberg gives you tools for doing that. So they give you the ability to kind of set up the way you update, the way you read and write tables, which we'll talk more about. Copy and write versus merge on read. You can take advantage of Parquet, Bloom filters, Z ordering your data, metrics collection, etc. And if you want to add even additional benefits to your Iceberg tables, you can take advantage of another open source project called Project Nessie. Project Nessie is one possible thing you can use as a catalog, which is actually built to be a catalog for Iceberg tables. And the nice thing is it extends that benefit. So basically at the table level within Apache Iceberg table, you're getting snapshots of the changes to the table. Well, Project Nessie is grabbing snapshots of changes to the catalog. So you're able to affect multiple tables at the same time. You can roll back multiple tables by rolling back your catalog. You can time travel across multiple tables using the commits at the catalog level. This also allows you to do branching and merging at the catalog level. And that branching allows you not only to isolate ETL work, but also to engage in multi-table transactions, because you can do transactions across multiple tables and then merge them all as one big atomic commit when you're done. That's pretty cool. Okay, so I'll talk more about Project Nessie as we go on. Okay, so yeah, okay, so we get an idea of what Iceberg is. Iceberg is a standard way of writing metadata. Engines can choose to read and write to that standard data, and it provides me with all these possible benefits like time travel, asset transactions, and so forth. Better query planning. So how about migrating to Iceberg? Again, to review, why I migrate to Iceberg. Again, you have the features. So you have things like partition evolution, which is only an Iceberg feature, not found in other table formats. Because you have compatibility mode, which is just referring to the fact that Apache Iceberg doesn't depend on the physical file structure of the files. So in that case, you can organize the files any way you want, which is really useful for object storage, because then you can take files in the same partition and split them up against multiple directories or prefixes to avoid throttling when you're requesting too many files from the same partition. You have hidden partitioning, which we'll talk more about a little bit later on, but it just makes partitioning easier to do and easier to take advantage of. Okay, so if you ever found partitioning tricky, Iceberg will make it easier. But it's not just the features of the format itself, it's the tooling. Okay, a lot of companies are giving support to Apache Iceberg, whether their tools support reading Apache Iceberg files or writing support files. So you have engines like Dremio, Apache Spark, Apache Flink, Presto, tools like Snowflake, Trino, all can work with Apache Iceberg tables. So the idea is you can figure, hey, what is the right tool for the job? Okay, there's going to be different use cases where different tools are going to work out better, and you have that flexibility in your data lakehouse when you're using Apache Iceberg. Okay, and that again, when you're dealing with that world of data that's just scaling and the use cases that are just constantly expanding, having that flexibility goes a long way. But on top of that, if you're using a Project Nessie catalog, okay, you get to take advantage of that Git-like isolation. Okay, so you can, make a branch, do transactions on your catalog of tables on that branch, and then merge them back in. But also, Nessie also has like aspects of security, and basically just makes your entire data world portable. So basically, I can take the same access rules and the same tables and move them from engine to engine. Okay. Uh, and then again, that's just only going to continue to expand with the level of granularity you have with security with Project Nessie a long time. So it's a really, really powerful tool. And the cool thing is, if you don't want to have to create your own Nessie service and stand it and maintain it, you do have a service like Dremio Arctic that can provide you that Nessie catalog and with a really nice UI and along with some table maintenance features. The project's open, okay? It's a very transparent project, okay? You can join the Slack, and the Slack isn't just helping people to use the format, but you can also see discussions about the development of the format there. Basically, all the development occurs on pretty much one repository, so it's really easy to track like who's contributing, what changes are being made, what changes are being discussed. They have very public meetings periodically to talk about advancements with a public document where you can see the notes from those meetings. So the point is you have large transparency on who's doing what and why in the project. So you don't necessarily have to wonder, hey, is this feature coming along? You have an idea of what's coming in the format, and you can plan how you work with the format around that and be active and part of the conversation. Okay, there's a wide variety of prominent contributors. Think Netflix, Apple, Dremio, many more companies are involved in the Iceberg project. Again, that active Slack channel where you can, again, go there to get assistance as a user, but you can also be part of that discussion of the development of the project. Okay, that's different than sometimes a Slack channel for other formats where it can oftentimes be more user support, but less a place to participate in the development of the project. Okay, now we get it. There's a lot of good reasons to migrate to Apache Iceberg. Okay, but one of the things you need is a catalog. You need a way to track all those Apache Iceberg tables, because one of the biggest benefits of Apache Iceberg is to be able to take your Iceberg tables from engine to engine, and sort of the unit for taking your bundle of tables from engine to engine is the catalog. It's the thing that says, hey, I got these 10 tables, I got these 20 tables, I got these 30 tables, and here's your metadata. So which one should you use? Now, of course, the prime option is generally going to be Project Nessie because it's built for that purpose. Okay, it's basically built to be a catalog, so it gives you not only the portability of your tables, but all those additional features like the Git-like functionality, catalog level rollback, and time travel. And again, you have the benefit that there's a cloud managed service providing you those, but you can also stand your own Project Nessie server because it is an open source project. So you could also just take that code, customize it to your needs, and deploy your own custom Project Nessie server for your purposes. Like any new technology, support for it is expanding. But right now, Project Nessie does have a pretty good list of support when it comes to engines, including support from Spark, Dremio, Flink, and Presto, and other engines constantly being added. And then right now there is a pending pull request for Project Nessie support in Trino. So in the meantime, you could take that fork, build Trino from the fork, and have Project Nessie support with a version of Trino. Okay, if you're not using Arctic, you must deploy your own, maintain your own Nessie server. That's one possible downside. But again, the cool thing about deploying your own Nessie server is you can customize the code. It's basically it's your server, and it's all open source, so it's all transparent and customizable, and all that good stuff. Now, you might be working on-prem, so in that case, probably one of your better options is going to be Hive because it might be one of the only options available to you, but it works just fine. The Hive Metastore can track directories, so it can track a file path and give you that, those concurrency guarantees that you would want when you're working with Apache Iceberg. Okay, so it's great if you already have one. So if you're already, working with an on-prem Hadoop cluster and you're using Hive and you have a Hive Metastore, this is a logical first place to start using Iceberg. If you don't have Hive already, well, then the downside is you'd have to deploy Hive, which may be in a situation where there isn't another catalog to use, depending on your particular infrastructure. If you're in the AWS ecosystem, you can use AWS Glue. Okay, and AWS Glue is also a great mechanism for like other services that sync to Glue to give you sort of a wider footprint. And it works well with all the other AWS services, so that way other AWS tools can easily see your Iceberg tables from the AWS Glue catalog. Okay, now if you're not using AWS, then the benefits of using AWS Glue are not as pronounced. But if you are in the AWS ecosystem, then AWS Glue as your Iceberg catalog makes a lot of sense. Now, there are a lot of other options, okay? I chose these three options just because generally they're right now they're generally the most supported as far as like different tools that support reading and seeing which tables you have from different catalogs. And that's a thing you have to think about when making a choice is, do the tools that I use can see the tables from the catalog of your choice. Okay. Um, Generally, all of them are going to be supported by Spark. Okay, HDFS is the file system catalog. That is actually even more well supported as far as like which tools can use it. But when you're using the file system catalog, the only issue with that is you generally want to avoid using that for production purposes if you have multiple concurrent writers, because you don't have this external catalog like Nessie, Hive, Metastore, or AWS Glue that's providing some sort of locking mechanism to give you those full ACID guarantees when you have concurrent writers. But it works. You can write Apache Iceberg tables as sort of like a directory on a file system. There's JDBC, where basically any database that supports a JDBC connection can be used to store those pointers, those references to different files. DynamoDB, there's an ECS catalog, and then there's the REST catalog. Now the REST catalog, let's talk about this one because it's unique. The REST catalog isn't necessarily a particular catalog implementation. It's a interface. So the idea is that the REST catalog is a standard REST API, and any service that implements that API can then be used as a catalog. So if you were to create your own custom catalog, okay, long as it implements this interface, you don't have to create a separate library to work with your catalog. You'd be able to just use the REST interface, the REST connection to connect to your custom catalog. Okay, so great if you want to create a custom catalog, you just follow the spec and you already have the support with any tool that supports a REST catalog connection. Right now there is a service that implements that. So right now the only catalog that I'm aware implementation that I'm aware of that supports the REST interface is from a company called Tabular, created by the founders of Apache Iceberg. And yeah, so that's one implementation that uses the REST catalog interface. But again, the idea behind the REST catalog interface is that anyone can create their own custom catalog, and if they implement those REST API endpoints, you'd be able to use that REST catalog connection with any engine that supports it. So that's just to kind of clarify what is the REST catalog. Okay, another issue that comes up when it comes to your catalog is your table migration. Okay, so what happens is you might start off with Hive Metastore, but then later on you decide you want to adopt Project Nessie. Okay, but now all your tables are in the Hive catalog. Well, recently there was a release of a table migration CLI tool that makes this really easy. You would just put in the stats in the CLI for your existing catalog and then the target catalog, and it will just literally move all those tables without necessarily moving the data to the new catalog. Okay, so making the idea of choosing a catalog less of a, this is a choice I have to stick with or I'm stuck with type situation. You can move between catalogs much easier nowadays. So that's pretty cool. Okay, then there's migration. So there's two approaches to migration. So when you think of migrating data, then one nice thing about Apache Iceberg is that it doesn't matter where the files are physically located. So it opens up the possibility of what's called an in-place migration. So the idea is you're going to keep the data where it is and just essentially write metadata around the existing Parquet files to make a table. Okay, which means you're not rewriting petabytes of data. That's pretty nice. But you could also do a shadow migration where you're going to create another copy of the table. That's the Iceberg copy of the table that kind of shadows the existing version of the table. So you are rewriting the data with the intention of migrating to the new table and then retiring that old version of the table. Okay, now either approach works and it's fine. There are pros and cons to either. So let's just talk about the tools, because Apache Iceberg gives you tools to help out with these sort of migration processes. Okay, typically in the form of Apache Spark procedures. So here are two Apache Spark procedures that currently exist. Okay, so first there's the migrate procedure, and the migrate procedure is particularly for Hive tables. So you have a table that is a Hive table that's in your Spark catalog, and you want to migrate that over to an Apache Iceberg table in your Iceberg catalog. you can use this migrate command. Now, keep in mind it is destructive. So after the command is done, the hive table no longer exists. So you don't want to run this until you're sure you're pretty ready to do it. So there's a separate procedure called snapshot that creates a temporary table, okay, for you to just kind of make sure that, hey, when this gets converted into an Iceberg table, this still works the way I expect it to work, okay? So you would first sort of use the snapshot procedure to create that temporary table from your hive table. And then once you've checked that everything has kind of been okay, then you would then run the migrate command to officially move that table over. That's if it's a hive table. Okay. Now, what if you have a bunch of Parquet files? So this could be a situation where you have Parquet files from a Delta Lake table, from a Hoodie table, or you just have a Parquet table, and you would want to now turn that into an Apache Iceberg table. This is where the add files procedure comes in. So you're not converting a hive table. What you're doing is you're saying, these Parquet files, I want them to be part of this existing Iceberg table. So you would create an Iceberg table with your desired schema that matches the Parquet files. And then what you would do is you'd run this command and say, give it either the individual Parquet files or a path of a folder of Parquet files, and it will then write the metadata to say that these files are part of a table. Okay, and then that will work. Okay, so you have that option where you can take the existing files and put them into a new Iceberg table. The only downside to that is you can't really change how the table is partitioned in the schema at that point because you're working with already written files. Now in a shadow migration, you are restating the data. The benefit is you can take advantage of this opportunity to change the way the data is structured, change the partitioning, change the schema to match what your needs may be now versus when the data was originally written. Okay, so you would just use create table as statement. So technically this can be done with any engine that can read Iceberg tables. Basically, whatever source of data you have, you can then just CTAS it over into an Iceberg table. Okay, so you could use something like a Dremio to CTAS pretty much data from anywhere into an Iceberg table, or Spark, or any engine you like. Okay, and then you can then change the partitioning as you like. Now, again, just kind of summarizing these methods, you would use migrate when you have a hive table. Okay, the data files are not going to be rewritten, but that means you can't really change the way the table is like partitioned or schema'd at that point. Okay, I think I might have just made up a word. Okay, cool. Now, add files would be used when you have Parquet files that are not part of a hive table, and you want to add them to an existing Iceberg table. CTAS, okay, basically that shadow migration approach where you're just basically rewriting the table, will rewrite the data, so you are using the compute to do that. But again, gives you an opportunity to change the structure of those files, the partitioning of those files. You can do that kind of stuff then. Now, if you're not migrating from not Iceberg to Iceberg, but instead you're migrating from one Iceberg catalog to another, then you would use the table migration CLI, which would then just basically move all those catalog references from one catalog to another, which shouldn't require any moving of any files. Okay, unless the catalogs are built on top of conflicting systems. So like, hey, you're trying to move to a cloud catalog, but you have your data on-prem, there might have to be some rewriting of files in that situation. But let's say your data is on S3 and you're just switching catalogs and the data can stay right there on S3. Basically, you can just run one command with the migration CLI, and it'll just switch the catalogs over, and works pretty well. Now, another concern is row level updates. Now, again, back in the days of Hive, you wanted to update one row, you had to pretty much update the entire partition. But with Apache Iceberg, you have some flexibility. Okay, you have two choices on how your table can do these like row level updates, these row level deletes. They can either do a copy on write style, okay, which would basically, if we updated one row, so let's say we wanted to delete one row in data file 003, okay, what it would do is rewrite data 003. So even though I'm only deleting one record, I'm rewriting every single record into a new data file, in this case, data file 006. And on the next snapshot, that file is included and data file 003 is not included. Okay, that works, but if you're only updating one row, that can get really expensive. For just one file, not so bad. But what if you're deleting like 10 rows, and each of those 10 rows are in different files. You're now rewriting 10 files to delete 10 rows. Okay, so it can get exponentially expensive if you're doing frequent and lots of these row level updates and deletes. Then there's merge on read. Now, the way merge on read works, so let's say I want to delete that record from data file 003. We keep data file 003. We don't rewrite the whole file. Instead, we're going to create a companion file called a delete file that says this record should be ignored. So that way, when that table is read going forward, the metadata will point out that this delete file exists for that partition, and it will be reconciled. So say, hey, when we read this file, make sure to ignore that record, so it's good as deleted without you having to write as much at write time. So if you save a little bit on the write, it does cost a little bit on the read because there is that extra step of having to reconcile that delete file. And in the Iceberg spec, there are two types of delete files. I would say the vast majority of times what you're going to see is our position deletes. And what these position deletes do is that within a particular partition, they're going to say, hey, in this particular file, ignore this the record of this position. So if it's the first row, position 0. And if it's like the 6th record, then position 5. And then what will happen is that, again, on read, when we read those files, we'll ignore those rows. Okay? This is a minimal impact on read speed because generally you just skip over the row when you get there and you know which row to skip over. So there's a little bit less moving around the different files. So, but there's also a little bit more work on the right side because you have to open up the file to figure out what that position is. So still faster than copy on write if you're doing lots of updates and deletes, but equality deletes will be even faster on the write, but even slower on the reads. Because with equality deletes, you're not even opening up the record. So you have no idea where that record is. You're just writing a file. The delete file just tracks the values that were deleted. So in this case, if I say, hey, I want to delete record with ID of 5, we just track that in the delete file, but I have no idea which file in the partition has record 5. So now when I read, I have to go read through all those files in the partition to see, hey, or if I read a file that has ID 5, I then have to skip over it, but I won't know it till I read it. So there can be a little bit more difficulty in the reconciliation on the read side. There's a really simple solution for this. It's compaction. Okay, the Iceberg libraries has a Spark procedure called rewrite data files, and now Dremio has a procedure called optimize, a SQL command called optimize. Both will let you run compaction on your table, which will then reconcile and clarify all these delete files. So that way, the data files that need to be rewritten are rewritten and won't affect reads going forward. So the idea is that when you're doing those updates, everything works out real fast, and then on the next compaction job, we clean all that up, keeping your reads nice and crisp. So imagine a situation where you're doing like hourly writes, okay? So you write the data every hour, or let's say you just have streaming data coming in. So you're doing a lot of these updates and deletes, and there's all these delete files coming up. What you can do is you can then schedule a compaction job that runs at the end of every hour that only compacts on the data created within the last hour, because you have the ability to kind of filter, hey, which data is going to be subject to the compaction. So that way you can run quicker compaction jobs on only the most recent data and keep things moving along. Cool. Now, in order to kind of like tweak the setting, like, hey, is it merge on read or copy on write? You would do so using the table setting called write.update.mode. Okay, or write.delete.mode or write.merge. The cool thing is it's not just, hey, one thing for the table. It's you can choose between copy and write, merge on read, depending on the type of transaction it is. A little side note about table settings is that generally, like, there's a bunch of different table settings that are part of the Iceberg specification. But at the end of the day, everything when it comes to the Iceberg spec, it's up to the engine that implements reading the Iceberg specification to honor any kind of table settings or make use of those table settings. So just because all these table settings, they do what they say they do in Apache Spark. Okay, because the Spark libraries are everything Spark-wise is built as part of the core Apache Iceberg project. But when you work with Apache Iceberg tables with other engines, you may want to look into sort of like how these settings are honored, whether they're honored on that particular engine. I would say over time, all engines will honor all properties, but again, over time as engines build out their support for the Apache Iceberg format. It's a thing that you should be aware of. Just because it's a setting in the specification doesn't mean every engine is aware of that setting in your table and honoring that setting in your table. Okay, so you might have merge on read set up in your table settings, but using another engine, they may write using copy on write. So just keep that in mind. Okay, so again, you have three different options: copy and write, which you should generally use if you're not doing many row level updates. So if you're just inserting a lot of data and there's no row updates or deletes, copy and write's fine. It's going to be the fastest for reads. Merge on read using position deletes is going to be sort of the best of both worlds when you're doing frequent updates and deletes. And then equality deletes will be sort of the most intensive for optimizing writes, which is typically the only time you're going to really see this currently in Apache Iceberg is oftentimes when you're ingesting data with Flink, because you're ingesting streams. So it's like real-time data. So you need that extra, you need to kind of make sure that you optimize that write latency. But then again, when if you are in a situation where you're using equality deletes, you want to make sure you run regular compaction on that data. So basically make sure that you're rewriting those data files into optimal sizes on a regular basis. Cool. Let's talk about partitioning in the Apache Iceberg world. Okay. So one of the coolest things about Apache Iceberg is the way it handles partitioning. Now there's partitioning evolution, which is a unique feature to Iceberg, allowing you to update how the table is partitioned whenever you'd like. Okay. And it doesn't require you to rewrite all the previous data. So essentially, whenever you change how the table is partitioned, it's going to change how all the data is written going forward. So any new data is written with the new partitioning scheme. And if you do any compaction and you rewrite data, any data that's rewritten is going to use the current partitioning scheme. Now, thing to keep in mind is the way partitioning is tracked is that generally in the metadata.json file, you have like an array of all the different partitioning schemes, which we can show you. Okay, so again, you're gonna have this array of partition specs, and each of those specs look like this. So it's basically a JSON object that has like, hey, what field is this partitioning on? What's the name of that field? And what is the transform? So what do I mean by transform? What used to happen is in Hive, if you wanted to partition by like day or month, you would have to create a whole separate column, a separate field. So that means you'd actually have to track a separate physical value for every record in the table and then partition based on that field. Okay, so one, you're holding more data in your tables, but on top of that, when the user queries a table, they have to make sure they filter based on those additional fields, because Hive will only know how to optimize the query if you filter based on that actual partition field. And we'll show you an example of that coming up. Okay, so basically Iceberg gives you all sorts of different like partition transforms that you can use. So for example, you have hour, day, and month, and year when it comes to time. And the cool thing about these is that unlike Hive, where you have to create like a separate month, a separate day, a separate year column to capture that granularity, if I choose year, it's going to be basically capture the year value. If I choose month, it's going to capture the month value. Okay, and if I capture day, it's going to capture the day value, including again the higher level, so the year. So day would include year and month. Okay, I don't necessarily have to specify day, year, and month. I can just specify day, and that's going to imply also year and month. Okay, which makes it nice and simpler. You just use the transform with the proper amount of granularity you want to capture. You can also do a truncate, so you can say, hey, I want to partition. Let's say I want to partition based on the first letter of everybody's name. I can say, hey, truncate to one spot, and it'll basically truncate based on the first letter of each field of each value. Or let's say I have thousands and thousands of potential different values, okay, and I really just kind of want to distribute it. I want it partitioned, so that way we get some benefit, but not thousands of partitions. Maybe I want 16 partitions. I can then use the bucket transform to partition it over a X number of buckets. And then basically use a hash function to distribute it across those buckets. Okay, and then identity just means you're just doing it based on the value of that table, so there's no transform. Okay, so to show you some examples, like again, you can change your partitioning. So once the table already exists, you can evolve your partitioning by just doing an alter table statement. So here I'm just saying, hey, we're going to partition this table going forward based on 16 buckets of the ID field. Okay, we're going to partition this table going forward based on the truncated value of the data field, but using only the first 4 spots, the first 4 characters of that field. Oh, for going forward, we're going to partition the table based on years. Okay, and we just choose it and bucket. And again, the idea is that you're not creating an additional column. So you don't, in your Parquet files, there is not an additional column where you're physically having to hold up data. All of this is tracked in the metadata files. In the metadata files, you're tracking ranges of partition values. So in this case, instead of tracking, let's say one record has 10,000, one file has 10,000 records, I don't have to track 10,000 partition, a partition column with now 10,000 values just for partitioning purposes. In the metadata file, in the manifest, we'll have a range of partition values for that column, saying, hey, this particular file has a range of X value to X value, and then that then trickles up to the manifest list, where it's going to say, hey, this manifest contains file value ranges from this column to this column, and you only have to apply this transform function on those ranges. Okay, so you're not transforming thousands of values, you're transforming a handful based on the ranges to figure out, hey, does this individual manifest or does this individual file apply to my particular partition for this particular query? Okay, long as you filter by one of the fields that has partitioning is based on. But just to kind of show you the old way, so again, you see here, when we created this table, we created an additional field called visit time, visit month, based on visit time. So we took a timestamp field and converted a month out of it, okay? And then we partitioned based on that month. Now, in order to take advantage of that partitioning, I had to include not only just saying, hey, give me the data between these 2 timestamps, but I have to include this extra query that says month 1, or else it's going to use all the data, which seems kind of silly because technically shouldn't these 2 timestamps kind of make that pretty obvious that I only want the data in January? But nope, because of the way it worked, you'd have to do that. And if you forgot to do that, guess what? You had a full table scan. So with Apache Iceberg, when I do the partitioning, I can just say, hey, partition based on month, based on this field. No additional field had to be created. And now when I query based on that timestamp field, Iceberg in its metadata is aware that we want to partition that particular field based on that value. So then when it looks at the ranges of data in the metadata, it can then apply that transform to figure out if the data is relevant or not, and how it's going to write the data. So very cool. Okay, then there's table properties. So as I mentioned earlier, like there's a bunch of standard table properties. For sure, they're all going to be honored in Apache Spark. In other engines, it'll vary. So things you want to investigate with the tooling that you're using. Generally, most of these generally only matter on the right side. Okay, generally, properly partition, well, an Iceberg table is going to get read the same regardless of what tool you use. Although again, some engines are going to have other optimizations that'll make queries with that engine even more performant. But the actual Iceberg planning generally is going to be done the same way. Cool. But in this case, again, setting table properties when you create a table is just adding this little table properties. And again, this is a Spark syntax snippet. So you would just set this table properties command, then just specify all the settings that you want to specify, as many as you want. Okay, so you can see, and then you can also alter those tables using an alter table statement to alter those table properties. Cool. Okay, now another setting you can have is Parquet vectorization. You used to default to being off or being false. It's now default to being on. So in this case, generally it's probably not a field you need to touch anymore, but generally you want that vectorization on. It's faster. Okay, so that will just make it faster at reading Parquet files because again, vectorization is just basically looking at it in a more columnar way, and that's generally what you ideally want. But again, it should default to on now. Then there's a write format, basically how you want to write the data. So for example, you may want to write the data to different types of files. So default is Parquet, but maybe you want to do delete files in a different format, like Avro. Okay, so you can choose sort of like, hey, how do you want to write the different types of files that Iceberg needs to write? Yeah, generally probably not much reason to go to change it from the defaults, which I think are these, Parquet and Avro, for delete files. But you know, you have that flexibility if you want to. Compression format, you can choose how the data is compressed. Okay, so you can choose between different compression formats like ZSTD, Brotli, 1Z4, gzip, Snappy, based on what's best for your particular use case and your particular data to get it compressed as much as possible. Cleaning up metadata files, this is a setting in what it'll do is that every time you make an update to the table, you create a new metadata file. That's that top level table-wide file. Okay, and eventually that kind of adds up. You're just adding, it doesn't necessarily affect the performance because you're not reading every metadata file every time you read the table, but it does affect storage. You're storing these files. So eventually you may want to clean them up. So this is a setting you can set up in your table where it'll say, okay, only retain, in this case, I'm only retaining 50 of these. So then what's going to happen is that every time a new metadata file is created, it's going to delete the oldest metadata file. So that we don't have to worry about that. Okay, there's column metrics tracking. Well, let's say you have a very wide table with lots of columns. You don't necessarily want to track all that metadata for every single column, especially if you don't filter on many of those columns. Okay, what's going to happen is that you're just causing what's called metadata bloat. So if you need to, you can customize how the metrics are tracked for each individual column, okay, through a pattern like this, okay. So here I'm saying, hey, don't track. So by default, don't track the metadata for a particular column. For column 1, I want you to track the counts. So it'll track like, the number of records, number of unique values, things like that. And then when I do a full metrics, it'll also capture like the range of values and a few other things, and that will be included in the metadata. So engines can use for planning purposes if it's there. Now, other properties to be aware of is that have significant consequences are things like write distribution mode. So essentially, when you're using Apache Spark, and generally most MPP systems will work in a similar way, what you're doing is you're splitting a job into several tasks. So each task is going to write their own files. So if I have data that isn't particularly well sorted, I might have let's say I have 10 partitions, and then each task, and I have 10 tasks, okay, and then each of those tasks got at least one record for each partition, okay. That means each task is going to write at least one file per partition. So you're going to get at least 10 files for each of those tasks. So 10 times 10, that's 100 files, when chances are all the data for one partition could have been stored in one file instead of 10 files. Okay, so you'll see this has in the past defaulted to none, which means it doesn't distribute the data between the tasks in any kind of particular way. It's going to assume that, hey, you're going to sort your data ahead of time. Which if your data is already pre-sorted, then that's good. But that's not always the case. So changing write distribution mode, and I think going forward, starting with like 1.30, it's going to be defaulting to hash. And if not, make sure you change it to hash. And what it does, it'll hash it based on partition. So that way, all the data of a particular partition should, depending on like the size limits of a task, will be in the same task. So that way, if possible, all the data from one partition will be in as few files as possible, being written by the same task, instead of being spread across multiple tasks. You'll end up getting a lot less files being written, and you're going to get much more better performance out of that way. Okay, so if you ever heard stories of someone writing to Iceberg and having way too many files being created, it's because probably write distribution mode was not set to hash. Then there's Parquet row group size and target file size bytes. Okay, so again, Parquet files have row groups, and row groups have metadata on the group that allows engines to determine whether they need to scan that row group or not. It's another way to speed up a query. So the more row groups you have, the more possible that an engine can prune a particular row group. But it also means a bigger file because you have the metadata for each row group. Less row groups mean you're storing less data, but is less likely that you're going to prune that particular row group. So here you can kind of set what you want as parameters of that. So you can say, hey, I want 1 gigabyte files. So this will say, hey, file size should be about 1 gigabyte, but I want 512 meg row groups. So that way it writes like 2 row groups per file. Or you can say, hey, I want 256 meg row groups, so it writes 4 meg row groups per file. You can kind of choose how you want to handle that. Okay, but that's what those two things do. And again, it just depends. If you have data, it's probably not going to benefit from predicate pushdown because generally you are scanning the full, big chunks of the table set of the table. Then maybe you'd rather there be less row groups because you rather just have less data in the file. But if you think you can benefit more from predicate pushdown more often, then you might want more row groups. Things to consider. Now, as you notice, there's a lot of knobs you have to turn to use, Iceberg and Spark. You have all these settings and whatnot. It gives you a lot of flexibility, but it can be a lot when you're first using Iceberg. Dremio, okay, makes Iceberg easy. Basically, generally the idea is that it's going to basically take a lot of those complications, a lot of those complex decisions, and figure out, hey, what is optimal for you? Okay, so it gives you just a lot of, basically you can just spin up Dremio and start running using icebergs right away, just using standard SQL without having to think so hard about setup and all this kind of stuff. You just connect a source that is a supported Iceberg catalog and begin running commands, which you have options like DDL, so you can create tables, alter tables using just normal SQL here in Dremio. There's this really cool command called copy into. Right now it supports CSV and JSON files. In the future, very soon, should be supporting Parquet files. But what it allows you to do is just take a file like a JSON file or a CSV file or a directory of files and say, take the values from these files and add them to this Apache Iceberg file folder. This Apache Iceberg table, and it will coerce all the values into the schema of that table. Okay, so you don't have to do any turning the CSV file into a table and then changing the schema of that table before you put it into an Iceberg table. You can just say, hey, this file into this table, it'll add those records, make all the type conversions, you're good to go. You have DML, okay, so you can do things like inserts, deletes, merge transactions, as you can see here. You can run all this right from Dremio. And the cool thing about Dremio is not only can you do this from the Dremio UI, but you can basically, you have a REST API interface, you have a Apache Aeroflight interface, a JDBC ODBC interface, so you can do it in notebooks. You can create cron jobs that send Dremio jobs on a set schedule. Using that REST interface. There's a lot of ways you can automate these things with Dremio as well. Okay, and send those jobs over to Dremio and just have it all nice and managed. Dremio takes full advantage of sort of Iceberg's layout to get the fastest performance possible. Technically Apache Iceberg is what allows reflections, which is a feature in Dremio, to accelerate pretty much any data set to work. Essentially, so essentially materialize, you can take a Postgres table that's connected to your Dremio, and it's going to create, when you turn on data reflections, create essentially an Apache Iceberg materialization that will allow you to accelerate the queries on that particular data set. So, Dremio really kind of takes Iceberg from top to bottom. There's the optimize command. So this is what I mentioned earlier, where basically Dremio has a command that will let you optimize your tables and essentially run compaction and take all those small files you may have accumulated and turn them into fewer, bigger files. So I can just say, hey, rewrite my data and just make sure that there's no files less than 100 and no bigger than 1,000 megabytes. Okay, and then it'll just create the appropriate files. There's vacuum. So again, once in a while, you're going to want to clean up old data in your Iceberg tables because data doesn't get deleted till you expire a data set, till you expire a snapshot. So you can just use this vacuum table command to say, hey, I want to vacuum the table, expire snapshots older than this particular snapshot timestamp. It'll expire those snapshots, and if a file is no longer associated with any valid snapshots, it's going to get cleaned up and vacuumed and deleted, saving you all that storage. But if you still have a file that was associated with that expired snapshot, but still expired with the a valid snapshot, this file will not get deleted. So basically, the data you want to have access to will still be fine, but the data you don't need can get cleaned up. And the cool thing is that Dremio works with a huge variety of catalogs, which is constantly expanding. So there'll always be, more catalogs being added that support Iceberg to Dremio every day. So you can, use Iceberg tables using AWS S3, AWS Glue, Google Cloud Storage, Azure Blob Storage, Hive, Hadoop, Project Nessie, and more. Okay, and basically you can use that to kind of access and view your catalog of Iceberg tables. And this is so basically you have robust access to Iceberg. Dremio makes it really easy to get started with Iceberg. And on top of it, you get all the other really cool Dremio features of the semantic layer, so that way you can actually add documentation, robust governance where you can kind of set row and column access controls, and make it really easy to give access to all your end users, access to all the data via Dremio's interfaces. So Dremio really makes having an Iceberg-based data lakehouse really, really easy. So definitely worth exploring. And again, also Dremio has a service, Dremio Arctic, which provides you that basically that hosted Nessie catalog along with table management, data lakehouse management features, which we'll discuss. So basically, this Dremio Arctic service, which allows you to create Nessie catalogs, and you can create as many as you want, which is Iceberg native, because again, Nessie is really built for cataloging those Iceberg tables. You can create as many catalogs as you want. So instead of having to stand a Nessie server for each catalog you want, you can just generate as many Nessie catalogs as you want. And this could be great for things like data mesh, where you may want to have a different catalog with different governance rules, different tables for each of your domains in your data mesh. Access control. Okay, you'll be able to create access controls from Arctic, and again, those rules will then be portable, to any engine that accesses that catalog. So it's not just Dremio will honor those rules, but Spark, Flink, Presto, etc. Okay, so you'll be able to have all this kind of access control, be able to kind of monitor and view, hey, these are the list of changes that happened to my catalog. I can see who made them, what did they do, get the commit ID, get this visibility into sort of the changes of your data sets in a nice, easy, intuitive UI. Okay, and remember we mentioned that optimize command that Dremio has that you can kind of run to optimize your table. You could set that on an automated schedule using Dremio Arctic. Also, that vacuum command that cleans up old snapshots, you can get that on an automated schedule. Okay, so you have these features, that are constantly being added and expanding. So you can use AWS Glue, you can use Hive to bring your Iceberg tables to Dremio, but if you use Dremio Arctic, you get the power of Project Nessie with this nicely integrated feature set that's managed for you and brings you a lot of nice bells and whistles with a really easy to use UI to really enhance your data lakehouse experience. Okay, and again, you get those benefits of like Project Nessie with the branching, so you can isolate your data and branches. The cool thing is you get with the UI, you can easily create merge branches, roll back your catalog. You can do that with just Nessie, but you have to generally do it from the CLI. Here you're getting a nice UI to kind of handle all those operations. But yeah, so this is going to bring this overview of Apache Iceberg to an end. Here's a QR code with more resources where you can watch more demos of working with Iceberg, working with Project Nessie, with Dremio with Iceberg. So scan that QR code if you want to keep learning. And thank you guys. Again, I'll do this again in a few months. You guys have a great day and enjoy.